Okay, good afternoon, everybody. I'm Marc Delcroix from NTT, and I will present you about target speech extraction. First, I want to thank my colleagues and collaborators that are listed here. In our everyday lives, we are often in a situation where we have several people speaking at the same time, such as in this picture. And we humans, we have the selective hearing ability, which means that we can attend to a specific speaker or sound signal in the scene and listen to that speaker. And this is realized using various clues, such as locational clues. We can focus on the speaker voice characteristics, or we can also use visual clues. And thanks to that, we can follow, for example, a conversation at a cocktail party. Target speech extraction, I will call it TSE in these slides, is a way to realize computational selective hearing. So as seen in this picture, we have a microphone that records the voice of several speakers and eventually also some noise. And the goal of target speech extraction is to extract from this mixture the speech only of a target speaker. And to inform the system which is the target speaker, we use target speaker clues. There are various speaker clues that can be exploited. For example, one can be audio clues. We can use audio clues, for example, a small enrollment, so a short recordings of the voice of the target speaker. Can be locational clues, so for example, the direction of the target speaker, or it can be a video, for example, the video of the mouth, of the lip movement of the target speaker speaking in the mixture. And in this talk, I will just focus on the audio clue-based approach. And before going into the more details into how we realize target speech extraction, I just want to show you a brief video. And there is a longer version of the video on YouTube, so if you're interested. So in this video, first we record the voice of the target speaker. In this case, it's me, like this. We first record 1 or 2 sentences containing only the target speaker's voice. We then use this recording to obtain the characteristics of his voice. And after, we extract the voice of the target speaker by using this enrollment, this pre-recording, to get the characteristics of the voice. And here I will just show one example of the extraction of the target speaker in a mixture of male and female speakers. SpeakerBeam uses the voice characteristics of the target speaker to extract his voice, even if it is mixed with the voice of other people. SpeakerBeam uses the voice characteristics of the target speaker to extract his voice, even if it is mixed with the voice of other people. So I hope you could perceive that we could extract the voice of the target speaker. So how we can realize that? Before explaining how we do it, I would like to mention that you could think of classical approaches to solve this problem. One simple way is if you have a microphone array, you can use a fixed beamformer. If you know the direction of the target speaker, you can extract the sounds from that direction, and that would do some kind of target speech extraction. However, since you need to know and have a fixed direction from the target speaker, this may lack in terms of flexibility. Another way you could think of solving this problem is to use separation. And separation, as shown in the figure here, it's separate a mixture into all of its source signals. And however, separation has a few drawbacks. First, to do separation, you require to know or estimate the number of speakers, which may not be always easy to do in practice. And also, there is speaker output ambiguity at the output of the system, which means that we don't know which outputs corresponds to the target speaker. So if you want to realize target speech extraction using a separation, you need to combine that with some speaker identification modules, and such a cascade connection may not be optimal. So instead, the approach I will describe here, try to directly perform target speech extraction by exploiting these target speaker clues to directly estimate the target speaker. And by doing so, we can avoid the limitation of the previous schemes. For example, we don't necessarily need to know the speaker position. we don't need to know the number of speakers in the mixtures. There is only a single output that corresponds to the target speaker, so there is no speaker output ambiguity, and we can globally optimize this framework. And this kind of approach have been made possible because thanks to deep learning, it's possible to optimize such a global system. And we saw in 2017 that it's possible to use audio clues to solve this problem. In 2018, there was some work showing that it's also possible to do target speech extraction with a video. And since then, there has been a rapid progress following the development of neural speech enhancement, separation, speaker identification, etc. And here I will first want to briefly explain the general framework that is quite common to all of the target speech extraction approaches. So usually the system consists of two parts. There is a speech extraction neural network, and there is a speaker embedding extraction module. So here for the speaker embedding extraction module, it accepts as an input a short enrollment. So it can be a few seconds of the speech of the target speaker. And from this enrollment data, it computes a speaker embedding vector that will represent the characteristics of the voice of the target speaker. And the speech extraction neural network is a network that will predict the extracted speech. And to do that, it exploits not only the mixture, but also this embedding vector so that the networks try to extract the voice in the mixture that match the characteristics found in the speaker embedding vector. So this kind of system does speech separation and speaker identification at once. So there are various ways to implement audio clue-based target speech extraction. And some of the implementation choice you can have and some of the implementation that have been investigated is to use different type of speaker embeddings. Some approach use a separated speaker embedding module that has been, for example, trained for doing speaker identification, or you can jointly learn the speaker embedding extraction and the speech extraction neural network. Also, for the extraction network, there are also different choice you can do. So one of the key parts of this network is the fusion layer. So this network consists in general of a first part of the network, the lower layers, which is a first extraction block. Then there is a fusion layer that will fuse the information from the mixture and from the speaker embedding. So this will guide the network towards extracting the target speaker. And then on top of that, there are also a few layers to actually extract the target speaker. So different types of fusion layer have been investigated. Also for the extraction blocks, you can use BLSTM, CNN, etc. And also frequency domain or time domain implementation have been proposed. And also regression or mask estimation based approach also have been investigated. So what I want to emphasize here is that the design choice of this network, basically what you can do is borrow the ideas of neural network speech separation, for example, and basically use similar architecture. The only difference is instead of using multiple output, you only have one output. And then you also need to have this fusion layer inside. But usually a good architecture that works well for speech separation will work also well for speech extraction. And here...
Sorry, Mark, on your screen, there is some block. Maybe it's due to the controller of the Zoom. Maybe you can move it somewhere else.
Yes, I try to. Okay, is it okay now?
Yeah, it's better now. Yeah.
Sorry.
No problem.
So I will just briefly present some result with SpeakerBeam and the implementation, which is time domain SpeakerBeam, which is one implementation for target speech extraction that we proposed at ICASP in 2020. And I mentioned that you can borrow approaches for speech separation, but this implementation follows the computational kind of implementation. So we have here the extraction network, and we have here the embedding network, and we jointly learn both networks together. So here we tested this approach on the multi-channel Wall Street Journal 2 mix. So it's a reverberant speech mixtures. And the results here are shown on in terms of signal to distortion ratio, SDR, in dB. So the higher the better. And in this figure, you can see here the SDR of the mixture. Then in this light blue, you have the performance when you do separation. And after separation, you choose the target speaker, which is match the best with the reference. So this is Oracle speaker identification on top of separation. But if you actually do a more practical way, is to actually do speaker identification on top of the separation, not Oracle one. And you see that if you do that, you have quite a significant drop in performance by more than 2 dBs. And compared to that, SpeakerBeams can get quite a good performance, which is even a little bit better than separation plus Oracle speaker identification in this case. So here I have a sound sample, but maybe I don't have too much time, so maybe I will skip it for now. But then also I want to emphasize that the code, we recently released it on this GitHub. So if you're interested, you can have a look at the code. And to finish the talk, I just want to mention briefly about some extension. And I think some people in the audience may be interested in non-speech signals such as sounds, events. And actually, it's possible to extend these ideas to do the target sound extraction. And for example, we have here in a picture, let's say if you walk in the street, you may have many sounds occurring. And some of them may be important to you and some other less important. So you may want to have a system when you inform it, for example, that you want to listen to the siren, if a siren occurs, that it will just extract the siren sound, but not the other sounds. And this can be realized using very similar ideas to what I've proposed, I've just explained for target speech extraction. And basically there are two main approaches that you can think about and that have been investigated. One is almost the same as the target speech extraction, but it's enrollment-based approach. So instead of dealing with speech mixture, you have a mixture of sounds, samples, and sound events, and you inform it which of the sound you want to extract by providing an enrollment, which is a small audio sample, a short audio sample of a sound that has similar characteristics to the sound you want to extract in the mixture. And by giving this enrollment, you can actually learn to extract the target sound. The other way to do it is, instead of using an enrollment, you actually inform the system with a class label, so what kind of sound you want to extract, and you can inform it with a one-hot vector. For example, if you want to extract harmonica sounds, then you would have a vector of zeros and only a 1 for the dimension that corresponds to the harmonica. And this way is also possible to realize target sound extraction. Recently at last Interspeech, I presented a way that mixed these two approaches also. I just want to show you a sound demo of this extension to sound extraction. So here we have a mixture of harmonica, shatter, and speech.
One of those things got in. Kill it. Bang.
So you want to extract the shatter, and this is the result. Or for speech.
One of those things got in. Kill it. Bang.
Okay, so it was a quite short overview of the field, but I presented briefly the idea of target speech and sound extraction, and I hope you could find it that is a promising way to tackle the cocktail party problem. The ideas I've proposed here, or I explained here, have been applied also to other problems: audiovisual extraction, target speaker ASR, where the goal here is to directly transcribe the speech without extracting the signal explicitly, and other applications. And here there is some links to the demo video. Also, there is a longer version of this talk because we presented a tutorial at Interspeech. So if you want to see the material, it's available here. Thank you.